Welcome to where time falls quiet.
When glaciers explode, 24 hours to drown the world. Take a moment to subscribe, so this place of calm is always here for you. Imagine waking up tomorrow to discover that everything you know about the transition from the last ice age to our modern world is built on a comfortable lie. Not a conspiracy, not a cover-up, but something far more unsettling. A collective assumption so deeply embedded in our understanding of planetary history that we never thought to question it. What if the Ice Age didn't end in the gradual, almost gentle way we've been taught? What if it ended in hours? The story you've been told is one of slow retreat, of glaciers melting incrementally over thousands of years, of sea levels rising at a pace so measured that life could adapt, migrate, and flourish in the newly habitable territories. It's a narrative of patience, of geological time moving at a rhythm so languid that human observation couldn't capture it. It's comforting because it suggests predictability, a planet that changes according to rules we can model and forecast. But comfort is not truth, and the evidence scattered across continents whispers a very different story. The last ice age, the Pleistocene glaciation, locked up so much water in continental ice sheets that global sea levels stood roughly 400 feet lower than today. Picture that for a moment, entire continental shelves exposed as dry land, coastlines extending miles beyond their present positions, river valleys that are now submarine canyons filled with air and life. The ice itself was not just frozen water sitting passively on the landscape. These were glacial systems miles thick, pressing down on the crust with such immense weight that the continents themselves deformed beneath them, creating geological signatures we can still measure today. The sheer volume is almost incomprehensible. Enough frozen mass to drown every major coastal city on Earth dozens of times over, held in suspended animation by temperature differences measured in mere degrees. Now here's where the silence begins to hum with implications. The transition from this frozen world to our present interglacial period is marked by a boundary in the geological record that doesn't behave the way it should if the thaw occurred gradually over millennia. Ice core data from Greenland and Antarctica reveal temperature spikes that happen not over centuries, but over decades or even years. Sediment layers in ocean floors show sudden influxes of freshwater glacial melt, creating distinct stratification patterns inconsistent with slow, steady warming. Pollen records from lake beds demonstrate vegetation zones shifting hundreds of miles in timeframes that seem biologically impossible under gradual climate change models. The evidence doesn't suggest a gentle awakening. It suggests a detonation. What would it take for miles-thick ice to release its grip not gradually, but catastrophically? The mechanisms are understood even if their full implications are rarely confronted. Supraglacial lakes forming on ice sheet surfaces, holding billions of gallons of meltwater that could drain through the ice in hours through a process called hydrofracturing. Ice dams containing glacial lakes the size of inland seas, holding back water under pressure that, once breached, would release floods making modern tsunamis look like ripples. Positive feedback loops where initial melting darkens ice surfaces, accelerating heat absorption and creating cascading collapse. These aren't theoretical scenarios from disaster films. These are documented geological processes with physical evidence preserved in landscape scarring across North America, Europe, and Asia. The channeled scablands of eastern Washington state tell a story written in bedrock. Here, the landscape bears wounds that geologists once refused to believe could be carved by water. The terrain shows features of catastrophic flooding on a scale that defies conventional river erosion. Massive coulees hundreds of feet deep, stripped to bare rock. Enormous ripple marks in gravel fields with wavelengths measured in hundreds of feet. Erratic boulders the size of houses transported dozens of miles from their source. For decades, the academic establishment rejected the flood hypothesis because it violated the principle of uniformitarianism, the idea that geological processes operate at constant, gradual rates. But the evidence wouldn't stay silent. The scablands were carved by the catastrophic failure of glacial Lake Missoula, releasing water volumes equivalent to the combined flow of every river on Earth, all at once, all in a matter of days. And that was just one lake, one ice dam failure in one region. The Laurentide ice sheet that covered most of North America held dozens of such marginal lakes. The Scandinavian ice sheet contained similar reservoirs. The geological record preserves evidence of at least 40 separate megaflood events during the last deglaciation, each reshaping vast landscapes in timeframes measured in hours to weeks. These weren't gradual releases. They were explosions of accumulated potential energy suddenly converting to kinetic destruction. But here's what keeps researchers awake at night, what the textbooks still struggle to fully articulate. If these localized ice dam failures could release such devastating floods, what would happen if an entire ice sheet experienced synchronous collapse? Not a single lake breaking through, but massive sections of continental glaciers losing structural integrity simultaneously due to a triggering event, whether volcanic activity beneath the ice, rapid atmospheric warming, or oceanic heat intrusion at marine margins. The mathematics are brutal. A rapid release of even 10% of the remaining Ice Age glacial mass would raise sea levels by 40 feet globally within days. Coastal zones inhabited by early human populations would vanish beneath walls of water moving too fast for escape, too vast for comprehension. The archaeological record contains an anomaly that mainstream narratives tend to minimize: a gap. A missing chapter between the flourishing of late Paleolithic cultures and the sudden emergence of Neolithic agricultural societies. The standard explanation attributes this to poor preservation, to the scarcity of sites from this transitional period. But there's another reading, one the evidence seems almost desperate to communicate if we're willing to listen. What if entire regions of human habitation, coastal areas that were the prime real estate of the Ice Age world due to abundant marine resources and moderate climates, were catastrophically inundated? What if the survivors weren't the majority, but scattered remnants who carried forward fragmentary memories of a world that drowned? Every major culture that emerged after this transition carries flood narratives in their deepest mythological layers. Not gradual sea level rise stories, but cataclysmic deluge accounts describing water arriving suddenly, overwhelming the world, drowning all but a chosen few. Mesopotamian epics speak of walls of water breaking over the land. Indigenous American oral traditions describe the Earth's surface being washed away. Mediterranean myths tell of divine floods punishing the old world. Ancient Chinese records document great inundations reshaping the landscape. These stories are dismissed as mythology, as moral fables about divine retribution. But what if they're traumatized cultural memory struggling to preserve a warning about something that actually happened? Something so devastating that it became encoded in every subsequent human society's foundational narrative. You're being told this because the question isn't just academic, it's existential. If the Ice Age ended not through predictable, modelable processes, but through catastrophic threshold-crossing events that transform the planet in days, then our understanding of climate stability is built on sand. The ice sheets that remain, Antarctica and Greenland, contain enough frozen water to raise sea levels by over 200 feet if fully melted. They sit atop volcanic systems adjacent to warming oceans, subject to the same physical laws that governed their Ice Age predecessors. The mechanisms that once triggered rapid collapse haven't disappeared. They're still there, embedded in the planetary system, waiting for the right pressure, the right trigger, to fire again. The silence before the flood isn't just about the past. It's about what we're not hearing right now, what the contemporary ice sheets might be trying to tell us through the language of crevasses widening, of ice streams accelerating, of meltwater pooling in places it shouldn't. The last ice age didn't end with a whimper, it ended with a roar. And somewhere beneath miles of frozen water, the detonator still ticks. The Laurentide ice sheet at its maximum extent was not simply a thick layer of frozen water sitting on the landscape like snow on a rooftop. It was a geophysical force of such magnitude that it literally deformed the shape of the planet beneath it. At its thickest points, this single ice mass reached heights of nearly 2 miles, roughly 3,000 meters of compacted glacial ice pressing down on the North American continent, with a weight exceeding 10 trillion tons per square mile. The crust beneath it sagged under this impossible burden, creating a depression so deep that even today, more than 10,000 years after the ice retreated, the land is still rising, still recovering from the trauma of being compressed by frozen water that transformed geology itself into something malleable. To comprehend the true scale of what we're discussing, consider this. The total volume of ice locked in the Pleistocene glaciation was approximately 52 million cubic kilometers. That number is abstract until you translate it into consequences. If you took all that ice and converted it instantly to liquid water, you would raise global sea levels by approximately 130 meters, or roughly 427 feet. Every coastal plain on Earth would vanish. The continental shelves that currently lie beneath shallow seas would remain submerged under an additional layer of water deep enough to cover a 40-story building. Cities, nations, entire ecosystems existing at current sea level would find themselves in the abyssal zone, crushed by pressure and erased from the surface world. But the Ice Age didn't hold all its water in a single monolithic sheet. The frozen mass was distributed across multiple continental glaciers, each a civilization-ending catastrophe waiting to happen. The Laurentide ice sheet covering North America, the Cordilleran ice sheet along the western coast, the Scandinavian ice sheet smothering northern Europe, the Patagonian ice sheet in South America, smaller but still massive ice caps in the Andes, the Himalayas, and across Asia. Each of these glacial systems operated according to its own dynamics, its own vulnerabilities, its own potential for sudden collapse. They were not synchronized clocks ticking down at the same rate. They were loaded weapons with different triggers, and the critical question is not whether they could fire simultaneously, but what would happen when even one of them did. The physics of ice sheet collapse is brutally straightforward once you strip away the academic comfort of gradual processes. Ice is not a static solid. Under sufficient pressure and with even minor temperature increases, it begins to behave as a viscous fluid, flowing under its own weight through a process called glacial creep. The bases of massive ice sheets rest on a thin layer of meltwater created by the pressure of the ice above and geothermal heat from below. This basal meltwater acts as a lubricant, allowing enormous ice masses to slide across the bedrock beneath them. When conditions destabilize this delicate balance, when meltwater production exceeds drainage capacity, or when ice dams fail at glacial margins. The entire system can transition from stable flow to catastrophic collapse in timeframes measured not in centuries, but in days. The Laurentide ice sheet alone contained enough water to raise sea levels by approximately 85 meters if it melted completely. But here's what the models struggle to capture, what the conservative estimates tend to minimize. We're not talking about complete melting. We're talking about structural failure. Imagine a dam not gradually eroding but catastrophically rupturing. The ice doesn't need to turn entirely to water to release its payload. It needs to lose structural integrity, to fracture along stress lines, to allow the pressurized meltwater trapped within and beneath it to escape suddenly. Historical analogues exist, preserved in the geological record with terrifying clarity. The Lake Agassiz outburst floods released volumes of water estimated at between 9,500 and 150,000 cubic kilometers in single events. These weren't trickles. These were oceanic masses of water suddenly injected into drainage systems designed for rivers, not inland seas. The mathematics of energy release in such events approaches the obscene. When glacial Lake Missoula failed, it released water at an estimated rate of 386 million cubic feet per second. To put that in perspective, that's roughly equivalent to the combined average discharge of all the rivers on Earth, all flowing through a single breach, all at once. The kinetic energy involved in moving that volume of water-carved channels hundreds of feet deep through solid basalt. The hydraulic forces were sufficient to transport boulders weighing hundreds of tons, dozens of miles from their source locations. And that was a relatively small glacial lake by Ice Age standards, holding perhaps 2,000 cubic kilometers of water. Lake Agassiz at its maximum extent held more than 160,000 cubic kilometers. Now scale that up. Imagine not a single lake failure, but a cascading collapse scenario where warming triggers simultaneous destabilization across multiple sectors of an ice sheet. The Laurentide had numerous marginal lakes, each held back by ice dams of varying stability. A failure in one sector could trigger failures in adjacent sectors through a domino effect of hydraulic pressure and structural stress. The ice sheet wasn't a monolithic block. It was a complex system of ice streams, frozen lakes, pressure zones, and stress fractures, all interconnected, all vulnerable to cascade failures. Once the collapse began, once the first major breach occurred, the subsequent failures wouldn't require additional warming or external triggers. The system would destroy itself through its own momentum, through the positive feedback loops inherent in catastrophic phase transitions. The weight of this frozen mass didn't just depress the crust beneath it. It stored potential energy on a planetary scale. Every meter of ice elevation represented stored gravitational potential that, once released, would convert to kinetic energy with perfect efficiency. The difference between frozen stasis and liquid mobility is temperature, and in the late Pleistocene, that difference was narrowing. Orbital forcing mechanisms, the Milankovitch cycles that govern Earth's relationship with solar radiation, had shifted. Insolation in northern latitudes was increasing. The equilibrium line, the altitude where snow accumulation equals ablation, was rising. The ice sheets were reaching a critical threshold, a point where the slightest additional forcing could tip the entire system from stable to catastrophic. Beneath the Laurentide ice sheet, the bedrock surface was not uniform. Large portions of the ice rested on land below sea level, particularly around Hudson Bay and the Great Lakes region. This created a marine ice sheet configuration where seawater could potentially intrude beneath the ice, lubricating the base and accelerating flow rates. Once marine intrusion begins, once warm oceanic water makes contact with the ice sheet base, the feedback becomes irreversible within the system's dynamics. The ice thins, reducing pressure, allowing more intrusion, accelerating melt, further reducing structural integrity. It's not a gradual process. It's a threshold-crossing event that, once initiated, proceeds to completion, regardless of subsequent atmospheric conditions. The Scandinavian ice sheet faced identical vulnerabilities. Much of its southern and western margins terminated in the ocean, creating calving fronts where icebergs would break off directly into the North Atlantic. As sea levels began to rise from initial melting elsewhere, these marine margins became increasingly unstable. Calving rates accelerate when ice fronts float, when they lose grounding contact with bedrock. The transition from grounded to floating ice is another threshold, another point of no return. Once an ice sheet's margin begins to float, it acts like a cork pulled from a bottle. The pressure behind it, the weight of miles of upstream ice, suddenly has a path of least resistance. The collapse propagates inland at speeds that exceed anything gradual warming models predict. Here's what the ice itself remembers, what the cores drilled from Greenland and Antarctica reveal in their layered testimony. The transition from glacial to interglacial conditions was not smooth. The ice cores show abrupt shifts in temperature, in atmospheric composition, in dust deposition that suggest the climate system doesn't slide gradually between states. It jumps. It flips from one equilibrium to another through mechanisms that operate faster than the orbital forcing that triggered them. These rapid climate shifts, documented in ice core records as occurring within decades or even years, correspond with periods of massive freshwater discharge into the oceans. The ice sheets weren't melting. They were collapsing, and their collapse changed not just the landscape but the planetary climate system itself, triggering feedbacks that amplified the initial forcing beyond anything predictable from the astronomical inputs alone. The weight of frozen time was not just physical mass pressing on continents. It was stored catastrophe, accumulated potential for transformation on a scale that makes recorded human disasters look like local incidents. Every cubic kilometre of ice represented thousands of years of accumulated snowfall, compressed under its own weight into crystalline structures holding atmospheric samples from ages past. When that ice released, it didn't just add water to the oceans. It injected ancient atmosphere, locked in gases, suspended sediments, and biological material into systems unprepared for the influx. The oceans received not gradual meltwater, but sudden injections of fresh water that disrupted thermohaline circulation. The great conveyor belts of oceanic heat transport. When those currents faltered, regional climates didn't adjust gradually. They plunged into chaos within years. And beneath it all, beneath the mathematical calculations and the geological evidence, sits an uncomfortable truth. The same physics that governed the Ice Age glaciers governs the ice sheets that remain. Antarctica holds enough ice to raise sea levels by 58 meters. Greenland holds enough for 7 meters. These are not historical curiosities. These are loaded weapons still sitting on the table, still vulnerable to the same triggering mechanisms, still capable of the same catastrophic release. The weight of frozen time hasn't disappeared. It's simply relocated, waiting for the next threshold to be crossed, the next trigger to be pulled. The process begins not with a bang, but with water pooling where it shouldn't be. Summer meltwater collecting on the surface of glacial ice, forming supraglacial lakes that shimmer an impossible blue against the white expanse. These aren't shallow puddles. At their peak extent during warming periods, supraglacial lakes on ice sheets like Greenland can hold billions of gallons of water, reaching depths of 30 meters or more, spanning areas measured in square kilometers. The ice beneath these lakes doesn't simply support the weight passively. It responds, it warms, it weakens. And when the structural threshold is crossed, when fractures propagate through the ice beneath the lake, the entire volume can drain in a matter of hours through a process glaciologists call hydrofracturing. Hydrofracturing operates through brutal efficiency. Water is denser than ice, and when it fills a crack or crevasse, it exerts pressure at the crack tip that exceeds the ice's fracture resistance. The crack propagates downward, driven by the hydraulic pressure of the water column above it. Once a supraglacial lake breaches through to the bed of the ice sheet, typically through a moulin or a pre-existing weakness in the ice structure, the drainage is catastrophic. Measurements from modern Greenland events have documented entire lakes containing billions of gallons vanishing in less than 24 hours. The water doesn't simply disappear into the ice. It reaches the bedrock beneath the glacier, pooling there, lubricating the interface between ice and stone, fundamentally altering the glacier's dynamics by reducing friction and accelerating flow rates by factors of hundreds of % within days. But supraglacial lake drainage is merely one mechanism in a cascade of processes that can transform stable ice into mobile catastrophe. Ice sheets contain internal plumbing systems of remarkable complexity. Englacial conduits, subglacial channels, and pressurized water systems that rival surface river networks in scale. During stable conditions, this drainage system efficiently removes meltwater, maintaining equilibrium. During rapid warming or when drainage capacity is exceeded, the system backs up. Pressure builds within the ice itself, creating hydraulic fracturing that doesn't just drain lakes, but fragments the entire ice structure. The ice doesn't melt away gradually. It falls apart structurally, losing integrity while still remaining largely frozen. This is the difference between ice melting and ice collapsing. And it's a difference measured in orders of magnitude in terms of timescale. The mechanics of ice dam failure follow a similar threshold crossing pattern. Consider the ice dams that impounded glacial Lake Agassiz along the southern margin of the Laurentide ice sheet. These weren't small barriers. They were ice structures hundreds of feet tall, miles wide, holding back water masses that rivaled the volume of all the Great Lakes combined. The dam's stability depended on the ice remaining cold enough to maintain structural strength, on the water pressure not exceeding the dam's resistance, on no flotation occurring that would lift the ice and break the seal with bedrock. Once any of these conditions failed, the breach sequence followed predictable physics. A small failure creates a notch in the dam. Water accelerates through the notch, enlarging it through erosive force and thermal melting. The enlarged breach allows more water through at higher velocity, which enlarges the breach further. This positive feedback loop proceeds to completion, draining the entire lake in days to weeks. The Lake Missoula flood sequence demonstrates this process with geological clarity. The lake formed when the Cordilleran ice sheet advanced south, damming the Clark Fork River Valley in what is now Montana. At maximum extent, Lake Missoula held approximately 2,000 cubic kilometers of water behind an ice dam at the present location of Lake Pend Oreille in Idaho. The dam was roughly 2,000 feet tall at its highest point. When it failed, it released water at flow rates estimated at 386 million cubic feet per second, creating floods that scoured channels through solid basalt, transported house-sized boulders, and deposited gravel bars hundreds of feet high across eastern Washington. The geological evidence suggests this happened not once, but repeatedly, perhaps 40 times or more during the last deglaciation. Each time the ice sheet advanced, it reformed the dam. Each time warming occurred, the dam failed catastrophically. The landscape remembers every iteration of this cycle. Now extrapolate these documented mechanisms to the full scale of Ice Age glaciation. The Laurentide ice sheet contained not one, but numerous marginal lakes held back by ice dams of varying configurations. Lake Agassiz was the largest, but Lake Ojibwe, Lake Barlow, and dozens of smaller glacial lakes rimmed the ice sheet's southern margin. Each represented stored potential energy. Each was vulnerable to the same failure mechanisms. The critical insight that mainstream glaciology tends to underemphasize is that these systems were interconnected. The failure of one dam could trigger hydraulic and mechanical stresses on adjacent dams. A cascade scenario wasn't just possible. Under certain warming conditions, it was probable. Once initiated, the collapse would proceed through its own momentum, independent of further external forcing. The process accelerates through mechanisms that compound rather than moderate. As ice sheet elevation decreases due to mass loss, the surface of the ice moves into warmer atmospheric layers, increasing melt rates. As glacial meltwater flows into the oceans, it raises sea level, which then intrudes further beneath marine terminating ice margins, accelerating calving and creating further mass loss. As ice thins, the pressure on basal water systems decreases, allowing more water to pool beneath the ice, further lubricating the bed and accelerating flow. Each of these feedbacks operates on timescales of years to decades, not millennia. Together, they constitute a system primed for nonlinear response, for rapid transition between stable and unstable states with minimal additional forcing required once the threshold is approached. The Younger Dryas event provides perhaps the most disturbing evidence of how quickly these systems can reorganize. Approximately 12,800 years ago, during what appeared to be steady warming out of the Ice Age, temperatures in the North Atlantic region plummeted back to near glacial conditions within decades. The cause, supported by multiple lines of evidence, was a massive outburst flood from Lake Agassiz that routed through the St. Lawrence drainage, injecting enormous volumes of fresh water into the North Atlantic. This freshwater pulse disrupted thermohaline circulation, the oceanic conveyor belt that transports tropical heat to northern latitudes. The disruption triggered a cascade: northern hemisphere cooling, ice sheet re-expansion, altered atmospheric circulation patterns, and ecosystem collapse across regions that had been warming. The climate didn't adjust gradually to the flood input. It flipped into a different state abruptly, remaining there for over a millennium before flipping back equally abruptly when circulation resumed. The Younger Dryas demonstrates that ice sheet collapse triggers don't just raise sea levels. They reorganize planetary climate systems. The freshwater injection from a catastrophic ice dam failure doesn't simply add to ocean volume. It stratifies the ocean's surface, creating a lens of fresh water that sits atop the denser salt water beneath it, preventing the normal sinking of cold water at high latitudes that drives the thermohaline circulation. When that circulation stops or weakens significantly, heat transport from the equator to the poles decreases dramatically. The result is regional cooling that can occur faster than warming, creating climate whiplash that exceeds any adaptation capacity for ecosystems or human societies. Modern ice sheet observations reveal these same processes operating today, not as historical curiosities but as active threats. Greenland's ice sheet is experiencing accelerating supraglacial lake formation, with lakes appearing at higher elevations where they've never been documented before. Hydrofracturing events are increasing in frequency. Ice flow rates are accelerating along major outlet glaciers. In Antarctica, ice shelves that buttress the inland ice are thinning and, in some cases, collapsing entirely, removing the structural support that prevents upstream ice from accelerating towards the ocean. The Thwaites Glacier, holding back enough ice to raise sea levels by over 0.5 meter, is experiencing basal melt rates that exceed model predictions, with marine intrusion occurring beneath the grounding line. The boundary between stable ice configuration and catastrophic collapse is not a distant threshold requiring massive, additional warming. It's a line that ice sheets approach asymptotically, where each increment of forcing has disproportionately larger effects as the system approaches critical state. The physics of this approach are well understood. Ice softens as temperature increases, not linearly but exponentially through the temperature-dependent flow law. A warming of just a few degrees can increase ice deformation rates by orders of magnitude. The transition from stable flow to rapid collapse is not gradual. It's a phase transition, like water turning to steam when it reaches boiling point. The temperature increase required is marginal. The response is total. When the ice breaks, it doesn't break politely. It doesn't send advance warnings or provide decades of notice. The geological record preserves the signature of these events. Abrupt shifts in sedimentation patterns, sudden influxes of ice-rafted debris in ocean cores, catastrophic flood deposits that bury entire landscapes under meters of sediment in single events. These are not anomalies in the data. They are the data, speaking clearly about the true nature of deglaciation. The Ice Age didn't end through patient thawing. It ended through structural failure of planetary-scale ice systems that crossed critical thresholds and collapsed under their own weight, releasing stored water and energy in timeframes measured in days and weeks, not centuries and millennia. The mechanics are understood, the evidence is preserved, and the same processes remain active, waiting in the ice that still remains. Hour 0. The breach begins not with thunder but with a sound like distant artillery, ice fracturing along stress lines that have been accumulating weakness for seasons. Somewhere along the southern margin of the Laurentide ice sheet, an ice dam holding back a glacial lake the size of Lake Superior reaches its failure threshold. Perhaps it's a supraglacial lake that has hydro-fractured through to the base, injecting pressurized water beneath the dam's structure. Perhaps it's rising temperatures that have weakened the ice below its critical strength. The specific trigger becomes irrelevant once the cascade begins. Water finds the initial breach, a crack no wider than a hand, and begins to flow. Within the first hour, hydraulic erosion has widened the breach to several meters. Water velocity through the constriction exceeds 50 kilometers per hour, carrying sufficient kinetic energy to scour ice and any sediment trapped within it. The roar of rushing water becomes audible for miles around the breach point, a sound like continuous thunder that doesn't fade. Animals in the vicinity, megafauna that have never encountered such phenomena, instinctively flee from the sound, from the ground vibrations, from some ancestral memory of water as threat rather than resource. The few human groups in the region, late Pleistocene hunters camped along what they believe are safe river valleys, hear the distant roar and feel the earth tremble beneath their feet. They don't understand yet. They will. By hour 3, the breach has become a chasm 50 meters wide, and the flow rate has increased to volumes measured in millions of cubic meters per hour. The lake behind the dam is beginning to drain in earnest, its surface level dropping visibly, several inches per hour initially, then feet per hour as the breach continues to enlarge. Downstream, in river valleys that have carried nothing more than seasonal meltwater flows, walls of water are advancing. Not the gradual rise of flooding, but moving fronts. Bores of turbulent water 5 to 10 meters high, traveling at speeds approaching 30 kilometers per hour. Everything in their path is swept away. Vegetation, soil, animals. Any human settlements unfortunate enough to occupy the valley floors. The water doesn't just flood, It scours, stripping landscapes down to bedrock in minutes. Hour 6 marks the point where cascade effects begin. The massive outflow from the breached dam is creating pressure differentials and structural stresses on adjacent ice dam systems. 100 kilometers to the east, another glacial lake held by a separate but interconnected ice structure begins to show signs of instability. Crevasses that had been stable for years suddenly propagate deeper into the ice. Subglacial water pressure spikes as the regional hydrological system responds to the catastrophic drainage occurring nearby. The ice dam here is thinner, more vulnerable. It won't hold much longer. Meanwhile, the initial flood has reached major river systems, overwhelming channels designed by geology for flows 1,000 times smaller. The rivers don't contain the influx. They overflow immediately, creating instant inland seas across floodplains that span hundreds of square kilometers. By hour 9, the second dam fails. Now 2 massive glacial lakes are draining simultaneously, their combined outflows merging in downstream valleys to create flood conditions that exceed anything in the geological record of gradual processes. The flow rates in some channels reach magnitudes equivalent to the combined discharge of all rivers on Earth, concentrated into drainage systems a few kilometers wide. The water carries not just dissolved sediment, but boulders, ice blocks the size of buildings, entire trees uprooted and tumbling in the turbulent flow. The erosive power is sufficient to carve channels through solid bedrock, creating canyons hundreds of feet deep in a matter of hours. The landscape is being rewritten in real time, transformed from one geological state to another with no transitional period. Hour 12 brings the thermal shock. The massive influx of glacial meltwater, near freezing temperature, begins entering the ocean at multiple points along the coast. In a single day, enough fresh water has been added to coastal waters to measurably alter salinity levels across thousands of square kilometers. The fresh water, being less dense than salt water, spreads across the ocean's surface like oil on water, creating a lens that blocks normal vertical mixing. This stratification has immediate effects on marine life. Fish populations that depend on specific temperature and salinity ranges begin to die off or flee the affected areas. Marine mammals surface gasping, confused by the sudden chemical change in their environment, but the biological impact is secondary to the physical one. The freshwater pulse is beginning to interfere with thermohaline circulation, the oceanic conveyor belt that moves heat from equator to poles. By hour 15, atmospheric effects become pronounced. The massive surface area of floodwater spread across formerly dry land is evaporating, pumping water vapor into the atmosphere at rates that exceed the regional climate system's normal capacity to process. Humidity spikes. Fog banks form over the expanding flood zones, reducing visibility to near zero across vast areas. The latent heat released by this rapid evaporation begins to alter local atmospheric pressure patterns. Winds shift as the atmosphere responds to the new thermal distribution. Storm systems that had been tracking along established patterns suddenly veer off course, their trajectories bent by the altered pressure gradients. The weather isn't just responding to the flood, it's being reorganized by it. Hour 18 marks the point where human populations begin to understand the scale of what's happening. Groups that had fled the initial valley floods believing they were escaping localized disasters reach what they thought were safe elevations only to see water still rising. The realization dawns: this isn't a flood in the traditional sense, this is the world transforming. Oral histories that will survive for thousands of years begin to form in these moments, as survivors watch landscapes they've known for generations vanish beneath water that seems to come from nowhere, that rises with impossible speed, that swallows everything familiar and replaces it with a hostile, churning surface that extends to the horizon. By hour 21, the coastline has begun to change measurably. The influx of meltwater, now joined by runoff from multiple simultaneous dam failures across different sections of the ice sheet margin, is raising local sea levels by centimeters per hour. This might sound insignificant until you consider the horizontal displacement it creates on shallow continental shelves. A 1 centimeter rise in sea level translates to horizontal advance of tens of meters on shelves, with gradients of 1 in 1,000. Coastal settlements, the prime real estate of the Ice Age world due to abundant marine resources, are experiencing what appears to be a rapidly advancing tide that doesn't recede. Groups living on these shelves, populations that might number in the thousands across affected regions, have hours to recognize the threat and move inland or face drowning. Hour 24. A full day has passed since the initial breach. The landscape across an area spanning thousands of square kilometers has been fundamentally altered. River valleys that existed for millennia have been scoured to different profiles. Lakes that held water for thousands of years have drained completely, leaving behind empty basins lined with fresh sediment. New lakes have formed in depressions created by the floodwaters, some of them large enough to be permanent features. The ocean has received enough freshwater input to create measurable changes in salinity across entire basins, and the collapse is nowhere near finished. Multiple other ice dams are showing signs of imminent failure. Destabilized by the same warming conditions that triggered the initial event, and by the hydraulic and mechanical stresses created by the ongoing drainage. The first 24 hours represents only the initiation phase of what could be a collapse sequence spanning weeks or months. Each dam failure triggers stresses on the remaining dams. Each pulse of meltwater into the ocean raises sea level incrementally, intruding further beneath marine terminating ice margins, accelerating calving and creating further mass loss. Each atmospheric effect compounds the next. Evaporation from floodwaters increases humidity, which increases cloud cover, which alters solar radiation reaching the surface, which affects temperature patterns, which feeds back into ice melt rates. The system has crossed into positive feedback territory, where each consequence of the initial event creates conditions that amplify subsequent events. For populations experiencing this transformation, the first day would be incomprehensible. The world they knew at dawn no longer exists by sunset. Landmarks vanished, territories drowned. The reliable patterns of seasons and landscape that had structured their understanding of reality dissolved in less time than it takes the moon to cross the sky. Those who survived would carry the memory forward, would encode it in their oral traditions, would pass down warnings about water rising from beneath the earth, about the sky opening, about the gods deciding to wash the world clean and start again. Because how else could you explain it? How else could you make sense of the day the planet reorganized itself while you watched, helpless to stop it, barely able to escape it, forever changed by surviving it? The archaeological record contains a peculiar absence, a gap that mainstream narratives tend to explain away with appeals to poor preservation, rising sea levels obscuring evidence, and the natural bias towards sites that survive rather than those that vanish. But absence is itself a form of evidence when the pattern is consistent, when the missing pieces share common characteristics, when the silence speaks louder than the fragments that remain. What if the gap isn't methodological? What if we're missing an entire chapter of human occupation not because the evidence weathered away gradually, but because it drowned catastrophically, buried beneath waters that rose too fast for preservation, too fast for escape? Consider the distribution of known Paleolithic sites from the period immediately preceding the end of the Ice Age. They cluster inland in cave systems, rock shelters, and elevated positions that survived the climatic transition. But here's what the distribution pattern suggests when you overlay it with Ice Age coastline reconstructions, the prime real estate, the most resource-rich environments of that world, were the exposed continental shelves. With sea levels 400 feet lower than present, these weren't marginal zones. They were vast coastal plains with abundant marine resources, freshwater river outlets, moderate climates buffered by oceanic influence, and game migration routes concentrated along the shelf margins. These would have been the places where human populations thrived, where population density was highest, where cultural complexity would have been most developed. And they're gone, submerged beneath hundreds of feet of water. The few sites that have been discovered on now submerged shelves reveal tantalizing glimpses of what was lost. Off the coast of Denmark, underwater archaeology has documented submerged forests from the late Ice Age, complete with preserved wooden artifacts and evidence of human activity. The Black Sea contains drowned settlements from when the sea was a freshwater lake, before a catastrophic marine intrusion flooded the basin. Off Japan, the Yonaguni structures, whether natural or artificial, sit at depths that would have been coastal zones during the Ice Age. These aren't anomalies, they're samples, rare glimpses of a vast archaeological record that exists but remains largely unexplored beneath the world's shallow seas. And the pattern they suggest is unsettling. Coastal occupation was extensive, and its disappearance was sudden. The timeline of sea level rise during deglaciation reveals periods of acceleration that exceed what gradual ice melt models predict. The meltwater pulse labeled 1A occurred approximately 14,600 years ago, raising sea levels by 16 to 25 meters in less than 500 years. That averages to over 3 centimeters per year, but the geological evidence suggests the rise wasn't steady. It came in pulses, in events where sea level jumped several meters in single years or decades. For populations living on low-gradient continental shelves, a 1-meter rise in sea level translates to horizontal shoreline retreat measured in kilometers. A pulse of several meters would advance the coastline inland faster than human communities could adapt or relocate their infrastructure. Imagine you're part of a coastal community in this world, living on what is now the submerged shelf off the coast of Southeast Asia, a region that during the Ice Age formed a vast landmass called Sunderland, connecting modern islands into a continuous territory. Your people have occupied this coast for generations, perhaps millennia. You know the tides, the seasonal patterns, the safe zones, and the dangerous ones. Then the water begins to rise. Not gradually enough to adjust your settlements each generation, but noticeably within single lifetimes. Elders speak of beaches that are now underwater. Fishing grounds move further out. Settlements are relocated inland, then relocated again. And then comes the pulse, the catastrophic acceleration when upstream ice dams fail and the ocean receives enough meltwater to jump several meters in a handful of years. The drowning would have been methodical and unstoppable. Tidal cycles that once predictably retreated now reach further inland with each high tide. Storm surges that used to threaten only the most exposed settlements now penetrate kilometers inland, flooding areas that had been safe for generations. Freshwater wells become brackish, then unusable, as saltwater intrusion advances through the soil. Agricultural zones, if any existed this early, become waterlogged and infertile. The infrastructure of coastal life, everything from fish traps to boat landings to seasonal camps, becomes unusable as the baseline of the ocean's position shifts upward by meters per decade. Eventually, the choice becomes binary: abandon everything and move inland, or stay and drown. The archaeological signature of such an event would be precisely what we observe: an apparent discontinuity, a gap where coastal populations should be but aren't, and then a sudden appearance of settled communities in inland locations with no clear local developmental sequence. The Neolithic Revolution, the supposed invention of agriculture and permanent settlement, occurs suspiciously close in time to the meltwater pulses and sea level rise of the deglaciation period. What if the Neolithic wasn't an invention, but a forced adaptation? What if populations that had achieved sedentism and resource management on the drowned shelves were forced inland, bringing their knowledge and techniques to new territories where the archaeological record begins because that's when they arrived, displaced by rising water? The flood myths encoded in virtually every major cultural tradition carry specific details that align uncomfortably well with catastrophic sea level rise scenarios. The Mesopotamian epics describe water rising from the abyss, overwhelming the land, forcing the few survivors to seek refuge on mountains or in boats. The biblical deluge account preserves details about duration, water sources, and the obliteration of previous civilization. Hindu traditions speak of successive worlds drowned by divine will. Chinese flood legends describe the Great Yu organizing efforts to channel floodwaters that threatened to drown the entire kingdom. Australian Aboriginal stories tell of when the sea rose and drowned the coastal lands, forcing people to the interior. These aren't moral fables that happen to use water as metaphor. They're traumatized cultural memories struggling to preserve a warning about something that actually happened. The specificity of these accounts is what makes them significant. They don't describe gradual sea level rise that communities adapted to over centuries. They describe sudden inundation, water appearing faster than escape was possible, the loss of entire territories within timescales short enough to be remembered as single events. The Sumerian king list divides history into pre-flood and post-flood dynasties, marking a clear threshold between two different worlds. The Epic of Gilgamesh preserves the account of Utnapishtim, who survived the flood and achieved immortality, becoming a link between the drowned world and the surviving one. Why would cultures separated by oceans and millennia preserve such similar narratives if not anchored in actual events that shaped their ancestral populations? Genetic evidence adds another layer to this picture. Population bottleneck studies suggest dramatic reductions in human genetic diversity occurring roughly 10 to 12,000 years ago, precisely when the major meltwater pulses were occurring. The bottlenecks don't show gradual population decline consistent with slow environmental change. They show rapid contractions suggesting sudden population loss, followed by expansion from surviving groups. The pattern suggests that human populations went through a crisis event, losing significant numbers in a short period, then recovering from a smaller genetic base. This is consistent with catastrophic coastal flooding eliminating large coastal populations while inland groups survive to repopulate the available territories. The distribution of haplogroups, genetic markers that trace human migrations, shows expansion patterns beginning in the post-glacial period that originate from what would have been inland refugia during maximum sea level rise. These populations spread outward, reoccupying coastal zones only after sea levels stabilized. It's as if humanity retreated inland during the crisis period, survived in scattered groups, then expanded back toward the coasts once the danger passed. The genetic geography we observe today isn't the map of where humans always lived. It's the map of where the survivors of the drowning re-established themselves, carrying forward fragmentary memories of the coastal world that was lost. The most unsettling aspect of this drowning scenario is its selectivity. The catastrophe didn't eliminate humans as a species, but it would have disproportionately affected the most developed populations. Coastal communities with established sedentism, complex resource management, accumulated knowledge, and cultural sophistication would have been the ones occupying the prime real estate that drowned. Inland populations, potentially more mobile and less invested in fixed locations, would have had better survival odds. So the world after the flood wasn't rebuilt by the most advanced pre-flood populations. It was rebuilt by the survivors, groups that might have been peripheral or less developed in the pre-flood world, but survived through luck of location or mobility. This creates a paradox in the archaeological record. The post-flood societies that emerge with agriculture, architecture, and social complexity appear almost suddenly, without clear local antecedents. The standard explanation is independent invention, that humans across different regions independently discovered agriculture and civilization. But what if they didn't invent it? What if they remembered it, imperfectly, from the drowned world? What if the survivors carried forward knowledge from coastal societies that were lost, attempting to reconstruct what they had seen or heard about in the territories where they now found themselves? The sudden appearance of sophisticated techniques wouldn't be invention. It would be restoration, the attempt to rebuild civilization from the memory of those who witnessed its drowning. The flood was just the opening act. What followed was a cascade of atmospheric and oceanic reorganization that transformed the planet's climate system in ways that exceeded the initial meltwater impact by orders of magnitude. The ice sheets weren't just water storage systems. They were climate regulators, thermal anchors that stabilized atmospheric circulation patterns through their sheer mass and reflectivity. When that regulatory infrastructure collapsed rapidly, it didn't just release water. It released the planet's climate from equilibrium, allowing feedback mechanisms that had been suppressed to activate simultaneously, creating a cascade of changes that fed upon themselves until the entire system reorganized into a new state. The first feedback to activate was albedo collapse. Ice and snow reflect approximately 80 to 90% of incoming solar radiation back to space, keeping the polar regions cold and maintaining the temperature gradient between equator and poles that drives atmospheric circulation. As ice sheet surfaces darkened with meltwater pooling, dust accumulation, and exposure of underlying rock and sediment, their reflectivity plummeted. Dark surfaces that were previously white began absorbing solar radiation instead of reflecting it, converting that energy directly to heat. This absorbed heat accelerated surface melting, which further darkened the surface, which absorbed more heat. The feedback was exponential, not linear. Each increment of darkening had disproportionately larger effects on melt rates. But the albedo feedback was merely the most visible manifestation of a deeper reorganization. Beneath the collapsing ice sheets, something far more dangerous was stirring. Permafrost soils, ground that had been frozen for tens of thousands of years, contained vast reserves of organic carbon locked in suspended animation. As ice sheet collapse and rapid warming thawed these soils, the organic matter within them became available to microbial decomposition. In anaerobic conditions beneath waterlogged thawing permafrost, this decomposition produces methane, a greenhouse gas with approximately 84 times the warming potential of carbon dioxide over a 20-year timeframe. The carbon bomb wasn't theoretical. It was detonating in real time across millions of square kilometers of newly thawed terrain. The methane release created a secondary warming pulse that exceeded the direct effect of increased atmospheric carbon dioxide. ice core records from Greenland show sharp spikes in atmospheric methane concentration occurring precisely during rapid warming periods of the deglaciation. These spikes correspond with periods of massive ice sheet retreat and permafrost thawing. The methane didn't just add to background greenhouse forcing. It triggered abrupt temperature jumps, regional warming events that occurred within decades, sometimes within years. The climate system wasn't sliding smoothly from glacial to interglacial conditions. It was jumping between states, crossing thresholds where positive feedbacks overwhelmed negative ones and drove rapid reorganization. Simultaneously, the oceanic circulation system was experiencing catastrophic disruption. The massive freshwater pulses from ice dam failures and accelerated melt weren't just raising sea levels. They were stratifying the ocean's surface, creating a lens of less dense freshwater sitting atop the saltwater beneath. This stratification prevented the normal sinking of cold, dense water at high latitudes, the process that drives thermohaline circulation. When that circulation weakened or stopped, the oceanic heat conveyor belt that transports tropical warmth to northern regions shut down. The result was paradoxical. Global warming from greenhouse gases and ice loss, but regional cooling in areas dependent on oceanic heat transport. The Younger Dryas cold reversal demonstrates this mechanism with brutal clarity. Following a period of steady warming and ice retreat, temperatures in the North Atlantic region plunged back to near glacial conditions within a matter of decades. The trigger was a redirection of glacial Lake Agassiz drainage from the Mississippi River outlet to the St. Lawrence, injecting massive freshwater volumes directly into the North Atlantic. This pulse disrupted thermohaline circulation, cutting off heat transport to northern Europe and eastern North America. Temperatures didn't decline gradually. They collapsed, dropping by 10 to 15 degrees Celsius in some regions within a few decades. The climate whiplash wasn't just rapid change. It was a flip to a different operational mode, maintained for over a millennium before the system recovered. The atmospheric circulation patterns responded to these oceanic changes with equal rapidity. The jet streams, high-altitude wind currents that guide weather systems and separate climate zones, are driven by temperature gradients between equator and poles. When those gradients change rapidly due to ice collapse and altered ocean circulation, the jet streams reorganize. They shift latitude, change amplitude, and develop blocking patterns that trap weather systems in place for extended periods. Regions that had experienced moderate, predictable seasonal patterns suddenly faced extreme variability. Floods followed by droughts, unusual cold intrusions into typically warm areas, storm tracks shifting hundreds of kilometers from their historical positions. The paleoclimate record preserves evidence of this atmospheric chaos in multiple proxies. Pollen records from lake sediments show vegetation zones shifting hundreds of miles within decades, then shifting back, then shifting again, responding to climate variability that exceeded anything modern forests have experienced. Speleothem records from cave formations show rapid changes in precipitation patterns, with monsoon systems strengthening, failing, and reorganizing on timescales of years to decades. Ice cores reveal dust deposition patterns suggesting major reorganizations of desert extent and atmospheric circulation strength. The atmosphere wasn't adjusting smoothly to the new boundary conditions created by ice loss. It was convulsing through a series of unstable states before settling into the modern pattern. The temperature swings during this period would have been incomprehensible to populations experiencing them. Imagine climate variability where a single human lifetime could span conditions ranging from near glacial cold to temperate warmth and back again. Winters that used to be predictable become deadly, then mild, then deadly again within decades. Growing seasons that supported specific plant communities suddenly fail. forcing populations to migrate or adapt to entirely different food sources. Water sources that were reliable become unreliable or disappear entirely as precipitation patterns shift. The ecological systems that supported human populations weren't just stressed. They were scrambled, reorganized so rapidly that adaptation through traditional knowledge became impossible. The megafauna extinctions that occurred during this period take on new significance when viewed through the lens of climate whiplash rather than gradual warming. Species that had survived multiple glacial cycles, that had proven their adaptive capacity through hundreds of thousands of years of climate variability, went extinct within a few thousand years of the deglaciation period. The standard explanation blames human hunting pressure, but the timeline is suspicious. The extinctions cluster during periods of maximum climate instability, when ecological systems were experiencing the most rapid reorganization. Perhaps the megafauna didn't fail to adapt to warming. Perhaps they couldn't adapt to the speed and unpredictability of change, to ecosystems that transformed faster than generational turnover could accommodate. The dust records from this period reveal another dimension of the chaos. As ice sheets retreated, they exposed vast areas of glacial sediment, fine-grained material ground to powder by glacial action, and left as outwash plains. Without vegetation to stabilize these surfaces, wind erosion mobilized enormous quantities of dust. Atmospheric dust loading increased by factors of 10 to 20 compared to pre-collapse levels. This dust didn't just reduce visibility, it affected radiative balance, nutrient transport, and precipitation patterns. Dust deposited on remaining ice surfaces darkened them, accelerating melt through the albedo feedback. Dust transported to oceans fertilized phytoplankton blooms, altering marine productivity and potentially affecting atmospheric oxygen and carbon dioxide levels through biological feedbacks. The methane release from thawing permafrost and marine sediments created hotspots of warming that exceeded global average temperature increases. In regions where methane clathrates, crystalline structures of methane trapped in ice within ocean sediments, became unstable due to warming bottom waters or pressure changes from altered ocean circulation. The release was explosive. Bubbles of methane rising from the seafloor created plumes visible at the surface, areas where the ocean appeared to boil as trapped gas escaped. The warming potential of these releases created regional climate anomalies, zones where temperature increases exceeded surrounding areas by several degrees, creating thermal stress on ecosystems that hadn't experienced such conditions in millions of years. The key insight that paleoclimatology struggles to communicate effectively is that climate change during deglaciation wasn't unidirectional. It wasn't simply warming replacing cold in a predictable transition. It was chaotic reorganization, a period where the climate system lost its regulatory stability and oscillated wildly between different states before settling into the interglacial configuration we now consider normal. The whiplash wasn't just rapid change. It was unpredictable, non-linear change where the direction and magnitude of shifts defied forecasting based on gradual forcing mechanisms. Populations experiencing this would have found their accumulated knowledge about climate patterns, seasonal timing, and resource availability suddenly obsolete, useless for predicting the immediate future. And here's what keeps contemporary climate scientists awake. The same feedbacks, the same destabilizing mechanisms that operated during the last deglaciation remain embedded in the current climate system. Permafrost still holds vast carbon reserves vulnerable to warming-induced release. Ice sheets still regulate climate through albedo and oceanic circulation effects. Methane clathrates remain stored in marine sediments at pressures and temperatures that could destabilize with continued warming. The difference is that modern human civilization, unlike Paleolithic populations, isn't mobile and adaptive. We're locked into fixed infrastructure, agricultural systems dependent on stable climate patterns, and population centers built around assumptions of gradual, predictable change. The climate system's capacity for rapid reorganization hasn't disappeared. It's simply dormant, waiting for the right forcing to trigger the cascade again. The question isn't whether anyone survived the catastrophic end of the Ice Age. Clearly, humans persist, which means survival occurred. The question is who survived, where they survived, and what they carried forward from the world that drowned. The genetic record suggests humanity passed through a bottleneck during the terminal Pleistocene, a period where effective population sizes contracted dramatically before expanding again in the Holocene. This isn't the signature of gradual climate adaptation. This is the signature of catastrophe, of large populations being reduced to small surviving groups that then repopulated available territories once conditions stabilized. The mathematics of population bottlenecks reveal uncomfortable truths about demographic collapse. Genetic diversity studies indicate that human populations went through a severe constriction roughly 12 to 10,000 years ago, with effective population sizes potentially dropping to tens of thousands globally. For a species that had spread across continents, that had occupied diverse environments from tropical coasts to periglacial zones, this represents a staggering loss. The bottleneck wasn't gradual attrition from resource stress. The loss of genetic lineages and the pattern of surviving haplogroups suggest rapid population reduction concentrated in specific regions, particularly coastal zones and lowland areas vulnerable to flooding and climate instability. Who were the survivors? Geography provides the first filter. Populations occupying elevated terrain, inland refugia, and regions buffered from the most extreme impacts of ice dam failures and sea level rise would have had survival advantages. Groups living in mountainous areas, river valleys away from maximum flood paths, and interior plateaus would have experienced the catastrophe as distant terror rather than immediate annihilation. These weren't necessarily the most culturally advanced or populous groups of the pre-catastrophe world. They were simply the ones fortunate enough to occupy ground that remained above the rising water, beyond the reach of the megafloods, distant from the zones of maximum climate chaos. The archaeological evidence from known survival zones reveals populations that demonstrate remarkable adaptability rather than technological sophistication. The groups that made it through weren't necessarily those with the most complex material culture, but those with the most flexible subsistence strategies. Hunter-gatherers with broad dietary ranges, populations that could shift between marine and terrestrial resources, groups with strong oral traditions for preserving environmental knowledge across generations. These were the characteristics that favored survival. Specialization was a death sentence. The populations locked into specific ecological niches, dependent on particular prey species or coastal resources, would have collapsed when their environmental foundations transformed beneath them. The Natufian culture of the Levant provides a glimpse of one survival strategy. Occupying a region that bridged multiple climate zones, positioned in highlands that remained viable even as lowlands flooded, they developed what appears to be proto-agricultural practices just as the Ice Age was ending. But here's the intriguing pattern. They didn't invent agriculture from scratch in a cognitive leap. They appear to have been managing wild grain crops, using grinding stones and storage technologies that suggest inherited knowledge rather than sudden innovation. Were they practicing techniques learned from now vanished coastal populations? Were they attempting to recreate food production systems they had witnessed or heard about before the catastrophe erased their sources? The temporal clustering of agricultural emergence across different regions, separated by thousands of kilometers, creates an uncomfortable pattern. Wheat and barley cultivation in the Fertile Crescent, rice cultivation in China, maize cultivation in Mesoamerica, all appear within a few thousand years of each other following the Ice Age termination. The standard narrative attributes this to independent invention, to humans everywhere, suddenly deciding to domesticate plants after hundreds of thousands of years of hunting and gathering. But the timing suggests an alternative reading. Survivors across different regions attempting to implement similar strategies, possibly derived from pre-catastrophe knowledge, adapted to whatever plants were available in their specific locations. The myth systems that emerged in post-catastrophe societies carry signatures of traumatic memory preserved through oral tradition. The flood narratives aren't just story templates. They contain specific details about the experience of surviving catastrophic inundation. The Mesopotamian accounts speak of receiving warning, of building vessels to preserve people and animals, of water covering the earth, of seeking high ground when the water receded. These details suggest transmission from populations that actually experienced rapid flooding, that actually made survival decisions in real time, that actually witnessed the world transforming around them. The myths aren't allegory. They're memory, imperfect and mythologized, but rooted in actual events that shaped the societies preserving them. The Australian Aboriginal oral traditions provide perhaps the most direct, preserved accounts of coastal drowning. Stories passed down through an estimated 400 generations describe specific coastal features now underwater, particular islands that were once connected to the mainland, the rising of the sea that forced people inland. These aren't vague flood myths. They're geographic accounts of landscape transformation that align with sea level rise data from the region. The ancestors who encoded these stories into oral tradition were witnesses to the drowning, survivors who carried the memory forward with enough precision that their descendants 10,000 years later can identify the drowned features being described. But survival wasn't just about being in the right place. It required social cohesion sufficient to maintain group function through trauma that would have shattered less resilient communities. The survivors needed to preserve not just individuals, but functional social units capable of reproduction, resource management, and cultural transmission. Groups too small would have faced genetic bottlenecks leading to extinction within a few generations. Groups too large would have struggled to feed themselves in the chaotic post-catastrophe environment. The optimal survival unit would have been somewhere between 50 and 500 individuals, large enough for genetic viability and labor division, but small enough to remain mobile and adaptable. The genetic signature of founder effects visible in modern populations suggests that many regional populations descended from very small founding groups that expanded rapidly once conditions stabilized. In Europe, the resettlement patterns following ice retreat show expansion from southern refugia, particularly the Iberian Peninsula, southern France, and the Balkans. These weren't gradual range expansions, they were rapid demographic explosions from small source populations that had survived in isolated pockets during the crisis period. The pattern repeats across other continents. Small surviving groups in refugia, followed by rapid expansion into territories that had been depopulated or rendered uninhabitable during the catastrophe. The material culture of immediate post-catastrophe populations shows interesting discontinuities with what preceded it. Tool technologies simplify, artistic traditions diminish or disappear. Social complexity, as measured by settlement size and architecture, reduces. This pattern could reflect the loss of knowledge and skills that weren't transmitted through the bottleneck. If the most culturally complex populations occupied coastal zones that drowned, their knowledge died with them. The survivors were starting over, not from zero, but from a reduced knowledge base, attempting to rebuild complexity from fragmentary understanding of what had existed before. Yet within this pattern of loss and simplification, certain knowledge seems to have been preserved with remarkable precision. Astronomical knowledge, calendrical systems, mathematical concepts. These appear in post-catastrophe societies with sophistication that seems disproportionate to their material culture. The megalithic structures that begin appearing in the early Holocene demonstrate geometric knowledge, astronomical alignment, and organizational capacity that exceed what the conventional narrative would predict for societies supposedly just emerging from hunter-gatherer lifestyles. Could this preserved knowledge represent inheritance from the drowned world, information carried forward by survivors and encoded in monuments designed to outlast the fragility of human memory? The survivors weren't random. They were selected by geography, by adaptability, by social cohesion, and perhaps by their position relative to knowledge networks that existed before the catastrophe. Small groups that maintained contact with multiple other groups that occupied positions along trade routes or cultural exchange networks would have had better access to diverse information and strategies. When crisis came, they could draw on a broader knowledge base for survival solutions. The groups that made it through were those positioned at information hubs, those capable of synthesizing knowledge from multiple sources and applying it flexibly to novel challenges. The emotional and psychological impact of surviving such a catastrophe would have shaped the survivors' worldview fundamentally. They had watched the world drown. They had seen landscapes they knew intimately vanish beneath water or transform beyond recognition. They had lost communities, knowledge holders, sacred sites, and entire ways of life. The trauma would have been encoded not just in individual memories, but in collective cultural psychology. The emphasis on cosmic disasters in mythological systems, the preoccupation with cycles of destruction and renewal, the persistent anxiety about divine punishment through natural catastrophe, these aren't primitive superstitions. They're rational responses from populations whose ancestors survived the unthinkable. And here's what the survival pattern reveals about the fragility of civilization. Complex societies occupying optimal environments are more vulnerable to catastrophic change than simpler societies in marginal zones. The coastal populations that likely possessed the highest population densities, the most elaborate cultures, the most sophisticated knowledge systems, these were precisely the populations most vulnerable to rapid sea level rise. The survivors who rebuilt the world weren't the most advanced. They were the most adaptable, the ones living in zones that happened to remain viable, the ones whose lower complexity paradoxically favored survival. The wreckage of the Ice Age world was inherited not by the strongest or the smartest, but by the lucky. Within a remarkably short period after the catastrophic flooding and climate chaos of the terminal Pleistocene, something extraordinary happened across multiple regions of the globe. Societies emerged that demonstrated capabilities seemingly disproportionate to their supposed developmental timeline. They appeared with sophisticated agricultural systems, monumental architecture, complex social organization, and mathematical knowledge that the standard narrative struggles to explain as independent invention by groups barely removed from hunter-gatherer lifestyles. The pattern becomes less mysterious when you consider an alternative framework. These weren't inventions. They were reconstructions, attempts to restore what had been lost, implementations of inherited knowledge by survivors trying to rebuild civilization from fragmentary memory. Consider Göbekli Tepe in modern Turkey, dated to approximately 11,600 years ago, placing it firmly in the immediate post-catastrophe period. The site consists of massive stone pillars carved with intricate reliefs, arranged in circular enclosures requiring organizational capacity and specialized labor that shouldn't exist according to conventional timelines. The people who built this weren't settled agriculturalists with generations of architectural experience to draw upon. They were supposedly mobile hunter-gatherers who decided to quarry, transport, and erect stones weighing up to 16 tons, carve them with sophisticated iconography, and bury the entire complex before building another layer on top. The cognitive dissonance of this timeline dissolves if these builders weren't inventing monumental architecture, but remembering it, recreating something they or their immediate ancestors had witnessed before the catastrophe. The astronomical alignments embedded in these early post-catastrophe structures reveal knowledge that exceeds simple observation. Göbekli Tepe's pillars align with celestial phenomena in ways suggesting understanding of precession, the slow wobble of Earth's axis that changes the position of stars over millennia. The mathematical precision required to encode such alignments isn't something discovered casually while arranging stones. It requires sustained observation over generations, mathematical systems for recording and calculating celestial positions, and cultural transmission robust enough to preserve this knowledge through catastrophic disruption. If this knowledge existed in pre-flood societies and was carried forward by survivors, the sophistication of immediate post-catastrophe monuments makes sense. They weren't learning astronomy from scratch, they were applying inherited understanding. The Sumerian civilization presents perhaps the most striking example of the restoration pattern. They appear in Mesopotamia around 5,000 years ago, not as a gradually developing culture, but as a fully formed civilization with writing, mathematics, astronomy, legal codes, and urban planning. The Sumerian king list explicitly divides history into pre-flood and post-flood periods, claiming kingship descended from heaven, was established in cities, and then was swept away by the deluge before being restored afterward. This isn't mythology struggling to explain cultural origins. This is a civilization stating explicitly that they understood themselves as inheritors of knowledge from before the catastrophe, as rebuilders rather than originators. The mathematical sophistication of early Mesopotamian civilization exceeds what gradual development would predict. They used a base 60 number system of remarkable elegance, allowing complex astronomical calculations and geometric constructions. Their astronomical tables tracked planetary movements with precision, requiring centuries of continuous observation to compile. Yet these tables appear essentially complete in the earliest phases of Sumerian literacy, as if they were being recorded from existing knowledge rather than discovered through contemporary observation. The implication is unsettling. The Sumerians were transcribing knowledge that existed before writing was reinvented, knowledge preserved through oral tradition or through survivors who had access to pre-flood astronomical records. The Poverty Point culture in what is now Louisiana demonstrates similar patterns of disproportionate sophistication appearing suddenly in the archaeological record. Dating to approximately 3,700 years ago, the site consists of massive earthwork constructions arranged in geometric patterns requiring surveying knowledge, astronomical alignments suggesting calendrical understanding, and organizational capacity to mobilize thousands of workers for purely ceremonial purposes. The culture appears with these capabilities already developed, builds for several centuries, and then abandons the site, leaving behind architecture that wouldn't be matched in North America for thousands of years. This isn't gradual cultural evolution. This is the appearance, flourishing, and disappearance of knowledge that seems disconnected from the surrounding developmental sequence. The proliferation of megalithic structures across Europe during the Neolithic period follows a similar pattern of sudden appearance without clear local antecedents. Stone circles, dolmens, passage tombs, and standing stones appear across landscapes recently deglaciated, constructed by populations supposedly just transitioning to agricultural lifestyles. These structures demonstrate geometric knowledge, astronomical understanding, and stoneworking techniques that appear fully developed rather than emerging through experimental phases. The standard explanation attributes this to independent invention across different regions, but the temporal clustering and technical similarities suggest transmission of inherited knowledge, techniques spreading from surviving groups to newly settled populations. The architectural precision of structures like Newgrange in Ireland or the alignments of Carnac in France encode astronomical and mathematical knowledge that required sophisticated understanding of geometry, celestial mechanics, and calendrical systems. These weren't primitive attempts at construction that improved over generations. The earliest examples demonstrate the highest levels of technical achievement, with later constructions sometimes showing declining rather than improving sophistication. This inverted development pattern makes sense if the earliest builders were working from inherited knowledge or under the direction of knowledge keepers who possessed information from before the catastrophe, while later generations gradually lost precision as the original understanding degraded through cultural transmission failures. The sudden appearance of agricultural systems presents a similar pattern of disproportionate sophistication. The domestication of wheat, barley, rice, maize, and other staple crops appears to have occurred within a remarkably compressed timeframe across different continents. The genetic changes required for domestication, the understanding of selective breeding, the development of cultivation techniques and processing methods, all this supposedly happened independently in multiple regions within a few thousand years of the Ice Age termination. But plant domestication isn't simple. It requires understanding of genetics, even if not formalized as such, recognition of heritable traits, patience to conduct selective breeding across multiple generations, and the social stability to maintain seed stocks and pass knowledge forward. Could this knowledge have been carried by survivors from coastal populations that had already developed agriculture before the floods? The distribution of linguistic families provides another piece of the puzzle. Language phylogenies reconstructed through comparative linguistics suggest that many major language families underwent rapid diversification in the early Holocene, spreading from apparent source regions that often correspond with elevated terrain or inland refugia. The pattern suggests small populations with distinct languages surviving in isolation during the crisis period, then expanding and diversifying as they repopulated available territories. But embedded within these languages are sophisticated vocabularies for navigation, astronomy, agriculture, and social organization that seem to predate the supposed invention of these practices. The words existed before the things they described were supposedly reinvented, suggesting the concepts were inherited from an earlier context. The mythology preserved in post-catastrophe cultures consistently references a golden age, a time of wisdom and peace before the great catastrophe, followed by a period of darkness and struggle, and then a restoration of civilization under the guidance of culture heroes or gods who taught essential knowledge. Egyptian traditions spoke of Zep Tepi, the first time when gods walked with humans and established the foundations of civilization. Mesopotamian myths describe the Apkallu, 7 sages who existed before the flood and taught humanity the arts of civilization. Mesoamerican traditions referenced Quetzalcoatl and other culture bringers who instructed in agriculture, astronomy, and architecture. These aren't fantasy narratives. They're cultural memories of knowledge transmission from a previous age. The pattern becomes clear when you strip away the mythological framing and examine the functional content. Post-catastrophe societies across the globe received or accessed knowledge that allowed them to implement sophisticated practices without the gradual development phases such practices should require. They built as if they remembered building. They calculated as if they inherited calculation systems. They organized as if familiar with organizational principles from previous contexts. The rapid emergence of civilization after the Ice Age wasn't humanity suddenly becoming clever. It was humanity recovering imperfectly and incompletely fragments of understanding that had existed before the catastrophe and been preserved by those who survived. The architecture of recovery wasn't just physical structures, though those remain as the most visible evidence. It was the reconstruction of knowledge systems, social organizations, cosmological understanding, and technological capabilities from the shattered remnants carried forward by survivors. Each megalith raised, each agricultural system implemented, each mathematical insight encoded, represented an act of cultural restoration. The builders weren't starting from zero. They were working from blueprints encoded in memory, oral tradition, and the inherited understanding of a world that had drowned, but whose knowledge refused to die completely, persisting through the determination of survivors to ensure that what was lost wouldn't be forgotten entirely. The mechanisms that triggered catastrophic ice collapse at the end of the Pleistocene haven't disappeared. They remain embedded in the planetary system, dormant but not extinct, waiting in the ice sheets that survived the last deglaciation. Antarctica holds approximately 26 million cubic kilometers of ice, enough frozen water to raise global sea levels by 58 meters if completely melted. Greenland contains another 2.8 million cubic kilometers, sufficient for an additional 7 meters of sea level rise. These aren't historical artifacts. These are loaded weapons still sitting on the table, governed by the same physics that controlled their Ice Age predecessors, vulnerable to the same triggering mechanisms that caused rapid collapse before. The West Antarctic ice sheet presents perhaps the most immediate vulnerability. Unlike the stable East Antarctic ice sheet, which rests on bedrock above sea level, much of the West Antarctic ice sheet sits on bedrock below sea level, creating what glaciologists call a marine ice sheet configuration. This matters because warm ocean water can intrude beneath the ice, melting it from below in a process that accelerates once initiated. The Thwaites Glacier, a critical buttress holding back a significant portion of the West Antarctic ice sheet, is experiencing basal melt rates that exceed model predictions. Satellite observations show the grounding line, the point where ice transitions from resting on bedrock to floating on water, retreating inland at rates of 1 to 2 kilometers per year in some sectors. Once a marine ice sheet begins to retreat, the physics of the collapse becomes self-reinforcing. As the grounding line retreats into deeper water, more of the ice base comes into contact with warm ocean water, accelerating melt rates. As ice thins, it loses the structural strength to resist flow, allowing upstream ice to accelerate toward the ocean. As more ice reaches the ocean and carves into icebergs, the removal of this mass reduces back pressure on the inland ice, further accelerating flow. This cascade of feedbacks creates what's known as marine ice sheet instability, a threshold-crossing phenomenon where gradual forcing triggers rapid, non-linear response that proceeds to completion regardless of subsequent changes in the forcing mechanism. The geological record from previous interglacial periods provides disturbing precedent for how quickly marine-based ice can collapse. During the last interglacial, approximately 125,000 years ago, global temperatures were only slightly warmer than present, yet sea levels reached 6 to 9 meters above current levels. The only plausible source for this much additional water is partial collapse of the Greenland and West Antarctic ice sheets. The rate of sea level rise during that period, reconstructed from coral records, suggests pulses of several meters occurring within centuries or even decades. The ice sheets didn't melt gradually over millennia. They lost mass through structural collapse occurring on timescales that would be catastrophic for modern coastal civilization. Greenland's ice sheet faces different but equally concerning vulnerabilities. Surface melt has been accelerating, with meltwater lakes forming at increasingly high elevations where they've never been documented in the instrumental record. These supraglacial lakes create the same hydrofracturing vulnerabilities that contributed to Ice Age collapse. When a lake drains through the ice, it delivers massive volumes of water to the bed of the ice sheet, lubricating the interface between ice and rock, reducing friction and allowing the ice to slide toward the ocean at accelerated rates. Multiple drainage events have been documented in recent decades, with some lakes containing billions of gallons disappearing within 24 hours. The albedo feedback that amplified Ice Age deglaciation is actively operating on current ice sheets. As surface melt increases, ice surfaces darken with accumulated dust, algae growth, and exposure of older, less reflective ice layers. This darkening reduces the percentage of solar radiation reflected back to space, increasing the amount of energy absorbed by the ice surface, accelerating melt, further darkening the surface. The feedback is exponential, not linear, meaning each increment of warming has disproportionately larger effects on ice loss rates. Observations from Greenland show areas of the ice sheet darkening substantially over the past 2 decades, with some regions seeing reflectivity decreases of 15 to 20%. Beneath the Antarctic ice sheet, another threat lurks in the form of subglacial volcanism. Antarctica isn't a geologically dead continent. It contains active volcanic systems beneath the ice, with at least 138 volcanoes identified, some of which are confirmed active. A significant volcanic eruption beneath the ice sheet would inject massive amounts of heat directly into the ice base, creating catastrophic melt from below that could destabilize entire sectors of the ice sheet within months. The warming would propagate through the ice, creating meltwater that would lubricate the bed and potentially trigger cascade failures across interconnected ice drainage basins. This isn't speculation. Similar scenarios occurred during the last deglaciation, with volcanic activity beneath ice sheets contributing to rapid collapse events. The ocean's role in ice sheet stability cannot be overstated. Warming ocean temperatures are increasing heat content in the waters surrounding Antarctica and Greenland. This warm water intrudes beneath ice shelves and marine terminating glaciers, melting them from below at rates that surface warming alone couldn't achieve. The process is insidious because it's largely invisible from satellite observation. The ice surface might appear stable while kilometers away, beneath hundreds of meters of floating ice, warm water is carving cavities and thinning the ice from below. By the time surface changes become evident, the structural damage is already critical, the point of no return already crossed. Climate models struggle to capture the full risk because they're built on assumptions of gradual processes and linear responses. The models treat ice sheet mass loss as a function of surface temperature and precipitation changes, applying physics-based calculations to estimate melt rates and ice flow. But they generally don't include the mechanisms for catastrophic structural failure, for threshold crossing events where small additional forcing triggers large, rapid responses. The models predict sea level rise measured in centimeters per decade. The geological record shows the ice sheets are capable of contributing meters per century or even per decade when structural collapse occurs. The permafrost carbon feedback represents another loaded weapon inherited from the Ice Age. Approximately 1,400 billion tons of carbon are stored in frozen soils across Arctic regions, roughly twice the amount currently in the atmosphere. As temperatures rise and permafrost thaws, this carbon becomes available for microbial decomposition, releasing carbon dioxide and methane into the atmosphere. The methane release is particularly concerning because of its high warming potential. Once the feedback initiates, once enough permafrost thaws to create significant methane emissions, the additional warming from those emissions thaws more permafrost, releasing more methane. The cascade becomes self-sustaining, independent of further human emissions. The question isn't whether these systems could cross critical thresholds. The question is when, and whether the crossing will be gradual enough to allow adaptation or rapid enough to overwhelm response capacity. Every increment of warming pushes the ice sheets closer to instability thresholds. Every year of rising ocean temperatures increases the rate of basal melt beneath marine ice margins. Every decade of permafrost thaw releases more carbon into feedback loops that amplify warming. The distance to the threshold is unknown, but the direction is clear, and the consequences of crossing it are written in the geological record with brutal clarity. Modern civilization is uniquely vulnerable to rapid ice sheet collapse in ways that Paleolithic populations weren't. Our cities cluster along coastlines, with over 600 million people living in areas less than 10 meters above current sea level. Our agricultural systems depend on stable climate patterns and reliable water sources. Our infrastructure, from ports to airports to power plants, is designed around assumptions of predictable sea level and weather. Our social systems lack the flexibility and mobility that allowed hunter-gatherer populations to relocate in response to environmental change. We've optimized for efficiency in a stable climate, sacrificing resilience in the process. The Ice Age didn't end with a whimper. It ended with a roar, with ice sheets collapsing in events measured in years and decades rather than millennia, with sea levels jumping meters in pulses that drowned coastlines faster than adaptation was possible, with climate systems convulsing through reorganizations that exceeded biological and cultural capacity to adjust. The same capacity for rapid, catastrophic change remains embedded in the planetary system. The ice sheets still hold enough water to drown our coastal cities. The atmosphere still contains the capacity for rapid reorganization. The ocean's circulation systems still have thresholds beyond which they flip to different operational modes. We tell ourselves the story of gradual change because it's comforting, because it suggests we have time to adapt, because it allows us to believe that the future will be a manageable extension of the present, with adjustments at the margins. But the Earth system doesn't respect our narrative preferences. It operates according to physics, according to thresholds and feedbacks that can transform stable configurations into catastrophic collapses within timeframes that exceed human response capacity. The ice sheets aren't melting on a schedule convenient for policy implementation. They're responding to physical forcing, approaching thresholds we can't precisely identify until we cross them. The detonator is still there, buried under miles of ice, waiting. Not waiting for anything in particular, simply existing in a state of conditional stability that depends on temperatures remaining below critical values, on ocean heat content staying beneath triggering thresholds, on the absence of volcanic activity in the wrong places at the wrong times. Every year we add greenhouse gases to the atmosphere, we push the system closer to those thresholds. Every decade of warming ocean temperatures increases the probability of marine ice sheet instability. Every increment brings us closer to the moment when the Ice Age ends again, not over millennia, but over hours, days, and years that transform everything. If you enjoyed the video, hit the like button, subscribe, and activate notifications so you don't miss our next videos.